Hello and welcome back to Physics for Future Leaders at Cal Maritime, and today we're looking at Milankovitch cycles. And remember, this is the second of the so-called solar cycles that we were going to look at as potential contributors to the climate of Earth. And in the Milankovitch cycles, there's actually a family of cycles, all discovered by the same, or theorized by the same guy, and subsequently confirmed by a number of simulations and historical temperature data and things like that. And the three cycles that are a part of this little family are first, cycles in the eccentricity of the Earth's orbit. So in other words, going from something that is quite circular, so the Earth here is the little blue ball, and this being the sun, which you probably figured out already. But a cycle in eccentricity means going from something that's pretty close to circular, not exactly for the Earth, but pretty close to circular, to something that's a little bit more ellipsoidal, a little bit more like an oval, and then back again, and back and forth, and back and forth, and back and forth, and back and forth between these two extremes in the Earth's orbit shape. The second family of cycles, in the family of cycles, is a cycle in obliquity, which I still stumble over. You can just think of it as a tilt. And what that means is that, say, this dotted line here is the vertical axis. Vertical means a little less when we're talking about outer space, but we'll call it vertical. And that's not the axis that the Earth rotates around. The Earth actually rotates around an axis that is right here, sort of offset from that vertical. And so this whole thing rotates around that axis. And the cycle that we're talking about here is one in which the tilt of the Earth goes from something that is maybe 20 degrees to something that's maybe 25 degrees. And we'll get a little more specific about that in a little bit. But it goes back and forth between those two extrema. And then the last of the three cycles that the Milankovitch cycles encompasses is a cycle called precession, or wobble, in which, as you can see here in the GIF, the axis of rotation, so this little red line that we had over here, that's equivalent to this little red line in the GIF, and that wobbles like a top, except in much slower motion, around the vertical axis for the Earth. Okay, so let's get a little more specific about the effects and why these occur for each one of these three cycles. Oh, and it's worth mentioning here, before we get into all those details, that taken together, these cycles can cause a variation of up to 25% in the solar energy received by Earth. This is a big deal. If you think about it, I mean, a 25% increase in the solar energy received by the Earth does cause a huge change in the climate of the Earth and its temperature. But as we will see, these cycles are not sufficient to explain the kind of temperature run-up we've had in recent years here on the Earth. So first, the eccentricity cycle. So eccentricity is the measure of how circular an orbit is. So an eccentricity of 0, so if we're looking over here, let me change my pointer color, is perfectly circular. So there's E equals, or eccentricity equals 0, perfectly circular. And then eccentricity equal to 0.5 is quite ellipsoidal. I mean, you can think of even more oval or ellipsoidal examples where you would have an orbit that looked something like this, like Halley's Comet or something like that, and that would have an eccentricity closer to 1. But once you get to 1, so we're looking here at this, this green line that I'm marking, eccentricity equal to 1 is a parabolic orbit. So that's the kind of orbit that you sometimes see where an object comes in, goes around something, but doesn't go into orbit around it and just keeps on keeps on going right out the other side. Okay? It's one example of an escape orbit. And as you go up in eccentricity, that orbit gets more and more. This is called a hyperbolic orbit. Again, it's an escape orbit, so something would not be, say, captured by the sun or captured by the Earth and go into orbit around it. It would just pass on by, just have its trajectory bent a bit by that thing. Okay? So those are the extremes of eccentricity. And the Earth really varies from something that's very, very close to zero. So this one's very close to zero eccentricity, to something that's a tiny, tiny fraction, nowhere close to even 0.5, just slightly ovalish for the second orbit here. Okay. Now, a few facts and figures about this cycle. Yes, the Earth's orbit changes, but it's not like it does it year to year. It does this with a period of approximately 100,000 years. So yes, this can affect our climate. It brings us considerably closer to the sun at what's called perihelion, so the closest pass to the sun. And of course takes us farther away at what's called aphelion. And that, because of the increase in solar energy you get when you're very close, that can affect global temperatures and how much solar energy we're getting and all of that kind of thing. But the variation between these two extremes, the whole cycle of circular to not circular and back, takes 100,000 years. And we're currently nearer to the maximum eccentricity, so most ellipsoidal, and decreasing. So we're headed back towards a more circular orbit. And at max eccentricity, the Earth receives about 20–30% more energy when closest to the sun, right, at perihelion, than when it's farthest away. That's a big difference. I mean, it's not still too far away from a circle, but it's a big enough difference that it's millions of miles farther away when you're farthest away, and millions of miles closer when you are closer. And so that means a very large difference in the amount of energy that the Earth receives from the sun. And this variation affects the length of seasons. So depending on which hemisphere is sort of pointed at the sun at various points during the orbit, it can shift the length of summer versus winter and things of that sort. And the primary cause for this cycle, this change in the Earth's orbit, is cyclical influences from Jupiter and Saturn's gravity on the Earth. They're quite large, nowhere near the sun. It's not like they're going to tear the Earth away from the sun and send it off someplace else, but they're enough mass to exert enough gravity on the Earth that it causes this kind of shift back and forth as Jupiter and Sun orbit around the sun as well. Now, the tilt cycle or obliquity cycle. Okay? Remember, that means that the Earth doesn't spin around a vertical axis, it spins around an axis that is tilted relative to that vertical. And the cycle between these two extremes, so tilted a little and tilted a lot, has a period of approximately 41,000 years. Again, a very long period of time. And that tilt varies between about 22 and about 24.5 degrees. And we're vaguely in the middle and headed towards the smaller one. Now this can have a pretty profound effect. It seems like a tiny little shift, but the tilt is the reason for our seasons, right? The fact that we have a tilt at all. And the variation, the change in the tilt, changes how different winter and summer are in each in the hemispheres, right? So, for example, if you have an Earth that was straight up and down, we wouldn't have any seasons at all, because we wouldn't have any variation in which hemisphere of the Earth was closest to the sun at any particular time in its orbit around the sun. And that if we have a tilt causes our summer and winter seasons, and if we have less of a tilt, then there's a lesser difference between the summer and winter seasons. And if we have a greater tilt, then we have a greater difference between the summer and winter seasons. And what that usually means is that at small tilts, that corresponds with accumulation of ice at higher latitudes. You can imagine, thinking back to albedo, the effect of albedo on the Earth. And if you haven't seen that video, go back and see that video. It should be in the playlist before this one. If you add ice at higher latitudes, well, ice is very reflective. Okay? It gives the Earth then a higher average albedo, and potentially reflects more solar light and solar energy back out into space before it has a chance to warm up the Earth. So that change, this change in tilt or obliquity, has that effect and sort of knock-on effect on the Earth's climate. And then lastly, precession, this idea that like a top, let me show you that, okay, sort of like a top, you have this wobble around the vertical axis. And one circle or wobble takes Earth about 26,000 years to complete. It's kind of a long time, a little shorter than the other two, but still an absolutely colossal amount of the time compared to human history. And it's caused by the tidal forces of the sun and the moon that shift the mass of the Earth around within the Earth, and that affects how it rotates. And it shifts the severity of seasons for each hemisphere. So remember that the tilt, the degree of tilt, change the severity of seasons just full stop for the whole globe. But right now, because the northern hemisphere is closest to the sun during winter, so our perihelion, where we pass closest to the sun, is like January 3rd or something like that on average, like about that. And so we get more incident solar energy when we're having our winter, and so our winters are more mild than the southern hemispheres currently are. But if you imagine over thousands of years, the Earth is going to precess, and so at different points in our orbit, it might turn out that thousands of years from now, and it will turn out that thousands of years from now, the southern hemisphere is going to be the one that's in its winter when we are at perihelion, and thus it will have a milder winter and a lesser difference between winter and summer than the northern hemisphere. There's also kind of cool thing, a different kind of precession called apsidal precession that does that, the gift there. So the orbit around the sun doesn't always have the same orientation. This is again due to the influences of Jupiter and Saturn in their orbits and the gravity they exert on the Earth. And the effect here is exaggerated, of course, sped up a lot, because apsidal precession has a period of about 100,000 years in terms of shifting all the way around the sun, as you see that oval shifting around there in the GIF. And those two things combined, the wobble, both kinds of precession, give you these kind of effects, and combine for an overall cycle that's, somewhere around 25,000 years in terms of its maximum and minimum in terms of its max and min effect on our climate. So, the takeaway from all of this is that the Milankovitch, pardon me, we'll go back to that slide. The Milankovitch cycles, okay, in their entirety, altogether, can cause huge variations in the amount of solar energy that Earth receives. And historically, based on all of our temperature proxy data and our reconstruction of the Earth's temperature history based on studies of all kinds of things that we have talked about and we will talk about a little bit more, they have these giant effects on climate. But the thing that often isn't mentioned when Milankovitch cycles are brought up in trying to cast doubt on climate science and the current state of it and what's causing this run-up in temperatures, humans or natural phenomenon, that kind of thing. Often Milankovitch cycles get trotted out as an example of, oh, well, here's this natural phenomenon that changes the solar energy hitting the Earth a whole lot, and that could be a contributing factor, and we shouldn't worry about our greenhouse gases. But this doesn't make any sense because, you can get to more complex arguments, okay? But it doesn't make any sense on its face because of how long all of these cycles take. We're talking at least tens of thousands of years for these effects to take place. And from max to min, we're still talking about 25%. So if we're only going through, over the past 50, 100 years, a tiny, tiny fraction of one of these cycles, the actual amount of solar energy that hits the Earth is going to change very little. And indeed, studies of the solar energy hitting the Earth have shown that actually in the last 20, 30 years, we're actually in a little bit of a downturn, even though for the last 100 years, we're sort of relatively high. So these effects, these cycles, though very important for our future climate and former climate, don't have any short-term effects that we as scientists have studied up until this point. So thanks for sticking with me through this 15-minute video. I will see you next time for more information on how it is that we reconstruct the temperature history of the Earth. See you then.